1.1. Perform the indicated conversion. 7 megaamps to kiloamps and 500 microwatts to milliwatts. For the first one, we see from the SI prefixes tables that capital M is equal to mega, which is 10 to the power of 6, and K is equal to kilo, which is 10 to the power of 3. We can then rewrite 7 megaamps as 7 times 10 to the power of 6 amps. Then, we can pull out 10 to the power of 3 to the right, and transform it into kilos. Therefore, we get that 7 megaamps is equal to 7 times 10 to the power of 3, or 7,000 kiloamps. For the second one, we see from the SI prefixes table that the Greek letter mu is equal to micro, which is 10 to the power of minus 6, and lowercase m is equal to milli, which is 10 to the power of minus 3. We can then rewrite 500 microwatts as 500 times 10 to the power of minus 6 watts. Then, we can pull out 10 to the power of minus 3 to the right, and transform it into milli. Therefore, we get that 500 microwatts is equal to 500 times 10 to the power of minus 3, or 0.5 milliwatts.
In this question 1.2, we need to determine the number of branches and the nodes. In this following circuit, we have to refer to what is the meaning of the branches and the nodes. So the branches is the element that connected in between the nodes, and it has two terminals. It could be the resistors or the voltage suppliers, or anything else that has two terminals between. And the nodes is the part that connected between two branches. If we understand the concept so that we could identify each part, and that we could facilitate it in determining when we use the nodal analysis and the mesh analysis in the later question. So this part is the important. Now let's look at the question in the following circuit. Now I'm going to highlight the part where it's the branches. So the branch is this resistor 1, 2 here. Also, don't forget the dependent suppliers as well. Now we can see that there are a total of 1, 2, 3, 4, 5, 6, 7 branches in this circuit. And how many nodes are there in this circuit? Well, be careful, because the nodes is the part that connected between each terminal of the branches. So if you see this part, the Y, it connects all of this. We count it as one. And this part it has, well, between this dependent source and the resistor. Now the other part is here, that connected between the dependent source and the two resistors. I'm going to keep highlighting the other part as well. As you can see, there are a total of 1 node, 2, 3, 4, and 5. So in the end, we have 5 nodes in total in the following circuit. And that's the answer of this question.
1.3. Apply superposition to find the current I. Superposition is a technique to find the current or voltage at any point in a given linear circuit, by considering the individual current or voltage contribution from each source in the circuit, then summing them together. In this case, we have two sources, a 20-volt voltage source and a 5 amps current source. Let us denote the current from the 20-volt voltage source as I1, and the current from 5 amps current source as I2. Then, we will analyze the current I1 first. Redraw the circuit with the 5 amps current source turned off. Remember that a current source becomes an open circuit once it is turned off. Here, we can see that the circuit becomes a simple series circuit. Thus we can find I1 using Ohm's law, current equals voltage over resistance. In this case, the voltage is 20 volts, and the resistance is 6 plus 4, which is 10 ohms. Therefore, we obtain that I1 is equal to 2 amps. Next, we will analyze the current I2. Redraw the circuit with the 20 volts voltage source turned off. A voltage source when turned off becomes a closed circuit. Then, we have a parallel circuit with a single current source. Hence, we can use the current divider formula, which states that for a circuit with two parallel resistors and a single current source, the current over one of the resistor is given by the current from the source times the resistance of the opposite side, divided by the total resistance of both resistors. In this case, the current from the source is 5 amps, the resistance on the opposite side is 6 ohms, and the sum of resistance is 10 ohms. Therefore, we obtain that I2 is equal to 3 amps. Lastly, the current I in the original circuit is the sum of current contributions from both sources, I1 and I2. Hence, I is equal to 2 plus 3, which is 5 amps.
In this question 1.4, the superposition principle can apply to the power calculation. Is it true or false? So we need to refer to the concept of the superposition, which applies linearity. We consider all different independent sources. Which each independent source contributing to the overall circuit, and we can apply this as, for instance, the voltage at the specific node A could equal to V and 1. By that it means that the voltage at the node A is in the sum of the voltage A considering one independent source at a time. Now, let's take a look how we can calculate the power. The power is equals to VI, I square R, and V square R. From the superposition, which is in the form of linear sum, can we apply the linear sum to the power calculation, like P output equals P output 1 from P output 2? The answer is no, because if we look at the specific part, I to the power of 2 and V to the power of 2, It's not it's not linear anymore. It's polynomial. So the answer to this question, can it apply? No, it's false.
1.5. For an ideal operational amplifier, which of the following statements are not true? A. The differential voltage across the input terminal is 0. B. The current into the input terminals is 0. C. The current from the output terminal is 0. Recall the two properties of an ideal operational amplifier. That is, 1. The differential voltage across both input terminals is 0. In other words, the voltage at both terminals are equal. And 2. The current flowing into both terminals is 0. Hence, choice A and B are true, and choice C is false, which is our answer.
In question 1.6, when the total charge in a capacitor is double, what is the value of the energy stored? Now to begin the step 1, we need two equations that represent the relation between the total charge and the energy. So starting with the first equation, Q that represents the total charge at that time in a capacitor equals C times V, the voltage that is applied to a capacitor at a specific time. Another equation is the work or the energy stored in a capacitor at that time equals 1 divided by 2 CV to the power of 2. We have these two equations. We try to minimize variable V so that we could represent this equation work in the form of only two variables Q and C. Now let's proceed with another step. We move the variable V. We get V to the equals Q divided by C. Now we substitute the variable here. We get work equals 1 divided by 2 times a capacitance times V, which is Q divided by C to the power of 2. We get 1 to the power of 2 times Q to the power of 2 divided by C. Now that we get the first equation, what we are going to do next is from the total charge, which we will represent it as Q1, and if it is double, we're going to define Q2 equals 2 times Q1. Alright? The next step, we refer the energy stored in the previous one before it is double equals to 1 to the power 1 divided by 2 times Q1 times C. Remember that the capacitance of the capacitor at different times is the same. Alright? Now let's take a look at W2. W2 is the energy stored if the total charge is double. So what we get, remember this relation. Work 2 equals 1 divided by 2 times Q2. We substitute this variable Q2 in here so that we could get the work of the total charge, which is double, in the form of Q1 times 4. Do you see something looks familiar with? You see this equation? We're going to sort it somehow. we're going to represent it as W1 because you see that it is totally equal to one another. We're going to get the work energy stored in a capacitor, which is equals to work 1 times 4. Now we get the relation. What does it mean by that? It means that the energy stored will be 4 times from the previous one. This is the conclusion that we get.
1.7. For the following circuit, if the current I is equal to cosine 4 times t, and the voltage V is equal to sine of 4 times t, determine whether the element is an inductor or a capacitor. There are two relationships to consider. 1. The voltage is equal to the inductance times the derivative of the current with respect to time. And 2. The current is equal to the capacitance times the derivative of the voltage with respect to time. As we are given the voltage and the current, we can use the two previous relationships to find the inductance and capacitance of the element. If the inductance turns out to be negative, then the element is a capacitor. Likewise, if the capacitance turns out to be negative, then the element is an inductor. Let's find the inductance first. Substitute V and I into the formula, then compute the results. We obtain that the inductance of this element is -1/4 Henry, which means that it is a capacitor. To be sure, we can also find the capacitance. Substitute V and I into the formula, then compute the results. We obtain that the capacitance is 1/4 Farad. Therefore, we can conclude that the element is a capacitor of 1/4 Farad.
Question 1.8. We have to prove the voltage divider formula from this following circuit. So this circuit is in series. So let me write this clearly. You can see that there is a current I flowing through this circuit. Now, what we know, first step, we have to know the relation between the voltage at the inductor and the amount of the current that has been flown through that inductor at the specific time. So we could write this as an equation. The voltage at the inductor at time t equals the value of the inductance as L times the derivative of I respected to t at the time specific t. Now we get the equation. The next step is looking at the circuit. It is in the form of series, right? So we could write it as V1, right? The voltage at that inductor at the first one, V1, I could write this as V1 equals L1 times derivative of I respective to t. That's the first equation. Now moving on, when we look at the second inductor, you can see that the amount of the current is equal along the circuit. So we could write it as V, the voltage 2 at a specific time of this inductor 2 equals the inductance L2 times derivative of I respective to t as equation of 2. You can see that this derivative is equal because it is in a series, right? Now we got two equations. We could combine it. 1 plus 2. Alright? We combine it, we will get the voltage V1 plus V2 equals I'm going to sort it somehow. Get the derivative of I with respect to t out in the form of times L1 plus L2. Now, I'm going to move this value right here. So it's going to be like this. Derivative of I with respect to t equals v1 plus v2 divided by L1 plus L2. Now we get this equation. So what we want to prove is the relation between the V1 and the V source. Now we need to refer to the concept of the Kirchhoff voltage law. So in this circuit, it's in parallel. Following on the line here along the circuit, we could get V1 plus, I could write this because it has the same meaning. V1 plus V2 is and minus V source equals 0. And then we get the relation of V1 plus V2 equals V source. This equation, now we could substitute this equation into equation 3. We will get the derivative of I respected to t equals the voltage source divided by the sum of the inductance 1 and 2. Alright, now we got this latest equation. What we want to do next is that we're going to substitute this equation in, we're going to solve this 3 prime in equation 1. Let me write here. So from equation V1 equals the inductance L1 times derivative of I divided by dt. So we substitute the value of the derivative of I divided by t. We will get the voltage 1 equals time the inductance of the first inductor times the V source divided by the sum of the value of the inductance of 2 inductors in the circuit. Now let's solve it. Now we get the equation that is following the voltage divider formula according to this question. And that's the end of our proof.
1.9. Prove that the formula for the summing amplifier is true. First, let us use Kirchhoff's current law on the node A, or the negative terminal of the operational amplifier. This yields the formula I1 plus I2 plus I3 equals I. Then, we can expand the formula using Ohm's law as follows. I1 is equal to V1 minus VA divided by R1. The same goes for I2 and I3. And I is equal to VA minus V output divided by RF. Then, notice that VA is equal to the voltage at the negative terminal of the operational amplifier. Assuming that this is an ideal operational amplifier, the voltage at both the negative and the positive terminals must be equal. Since the positive terminal is grounded, it is equal to 0 volts, and thus the negative terminal, or VA, is also equal to 0 volts. Substituting this into our previous formula, we obtain exactly the formula for the summing amplifier. Therefore, we have proven the given formula.
In this question, we want to prove that the maximum power transferred to the load occurring when the load resistance equals to R, and the maximum power is corresponding to this formula. Now, the first step that we need to do is we need to find the P or the P value in terms of RL, or the power occurring at the load. To do that, we need to find I the amount of the circuit, the amount of the current applied to the circuit, which according to the Kirchhoff voltage law, we would get I equals to V divided by R plus RL. And the power in terms of the power corresponding to this load equals I to the power of 2 times RL. Then we substitute this value. Now, as you can see that this power occurring at the load, which is represented as a function, in this case function, respected to RLUC. In that case, when we want to find the maximum of this value, the Pmax, considering at when we studying at in the calculus, the Cal 1 or the Cal 2, I'm not sure, the maximum of the function, or we may refer to it as a critical point, occur when, in this case, the derivative of P, the power occurring at the load, respected to RL, equals to 0. Within this statement, we're going to simplify the equation of the derivative of power respected to RL. Now let's proceed. Then we get the derivative of power respected to RL equals to, we have some constant V to the power 2, which we could remove it out. Then we get now, according to the division, when we consider the derivative of the division components, what we get is we will, so we put it, the lower one here, to the power of 2 times the derivative of the upper one minus the multiplication of the upper one times the derivative of the lower one, or we call the divisor, as I would say, respected to RL, and the overall divided by R plus RL to the power of 2, no, to the power of, then to the power of 2. Alright, let's simplify it. This part equals to 1. This we could use chain rule. Okay, this one minus RL times, if you remember chain rule, we could write it as this case. Now, what we get here, Let's keep this. Do not just expanding this formula first, because you will know it in the end. This part, this will get 2, right? 2 times r plus rl, and this is equals to 1 of them divided by r plus rl4. Let's keep it this way, even though we can simplify it more, but you will know the risk behind it. Now, according to this formula, we want to find the critical point occurring when the derivative of this function equals to 0, right? Now let's apply that condition. Then we get, let's copy this equation. Which equals to 0. Sorry, my bad. I think I used too much space. Let's just, to make it smaller, resize. Now let's focus this part. As you can see that when we have division equals to 0, we can just normally cut this part out because it's not affecting our solution. Then in that case, we get times 2 times r plus rl. Then we remove the conjugation part. And what we get is the remainder of this formula. Now you can see that there are two cases. The critical points occur when r equals minus rl from this part, and r equals, or r equals rl from this part too. You can see that this case is not possible, because in the real world, the value of the resistance could not be the negative, right? So we left with the only one case, which is the r equals to rl, or the road resistance is equal to the r. Then, as we have already found the critical point and the condition itself, now let's find the maximum power occurring at the load resistance, which we have already made the equation. If you remember, it equals to p to the power times rl divided by r plus rl, and want to find p max when rl equals to occur. Let's use this condition. Then we get p max equals to v to the power times rl divided by r. Let's assume that we substitute this condition already. Then we get r divided by r plus r. You see the highlight part right here when referring to this condition. Then what we get I think there's some typo here. That's great. Okay, 2r to the power of 2, we get 4r to the power of 2. Cut this part, then we'll get the final solution, which the power maximum occurs, and the value itself equals to the v to the power 2 divided by 4, which corresponding and accordingly to the formula of the question. And this is the proof of this question 1.10. Now let's take a look at this question 2 here. We want to find the current that flow through this resistor, right? And also that we want to find the power generated by the source in this network here. So first of all, what we know right now is that we could not comprehend or calculate the total resistor directly. So what we need to do is that you can see the structure here, and it's similar to the Y to delta transformation. And as you can see that if I'm going to apply this part so that I could calculate the resistor, the total resistor easily, as I'm showing it right now, the formula representing this total equivalent resistor in just different form. And you see that I'm transforming delta to Y in this case, and the formula corresponding to this case is, let me put it here. So you may be confused, but RB and RC in this case is just the compound resistor corresponding to this location, and all of them divided by all sides, the total sum of all sizes of resistor. Now, to not make it more confused, let's just draw it again. Alright, this actually looks better. Okay, so we're going to find R1 and R2, right? So R1, it's equals to 4 times 12. Remember the unit is kilo ohms, right? And also divided by the total sum, which equals to 48 times divided by 22, which is equals to 2.18 kilo ohms. And let's find R2 and R3 as well. For the R2 part, we times 6 times 12 divided by the total sum. What do we get? Get 72 divided by 22, and the result is 3.27 kilo ohms. And R3 is equals to 6 times 4 divided by 4 plus 12 plus 6, which is equals to 24 divided by 22. Alright, now we got everything right here, and to find the equivalent circuit of this part is going to be easy, right? Because we know that this part is connected in series, and also this part is connected in series, and then the overall is connected in parallel, and then connected in series again with R3. So let's find the R equivalent for this part, which is equal to let's write it more simple here, 6 plus R1, and all of them parallel with 18 plus R2, and then the overall plus R3. So for the case of 6 plus R1, we could write That is a formula, and you should probably remember it as 6 times R1 times 18 plus R2, and then all of them divided by the total sum, 6 plus R1 plus 18 and plus R2. Alright, now let's substitute everything that we have here. So in the end, if we substitute everything, now the answer will be about 7.00 kilo ohms. Okay, then what do we get here? We get that, let's write the simple circuit again. Now that we got this part here, so we want to find the current, right? We can use the KVL from the overall circuit, which is equals to I equals to the current voltage 120 divided by the total sum, which is equals to 5 past 7. Remember, the unit is kilo, so that we have to multiply with the 10 to the power of 3 as well. And in the end, we get the result, which is equals to 0.01 amperes. And that is the answer to the question 1 here. Now we got the amount of current that flown through the circuit. Question 2, we want to find the power generated by the source, right? So I got no space. Let me minimal it again. Let me resize. It. So we got the current that flown, right? And to find the power generated by the source, as you see that in this part, we got the current that flown to the other side, the -1. So normally the power of the generated source usually be in a negative sign because of how the rule works of the current that flown to the other side of the source. So in the end, we get that the power is equals to minus V and the I that flown to that voltage source, which in this case is equals to minus 120 and multiply with 0.01, and then we get minus 1.2 watts. So in the end, the power generated by the source is 1.2 watts. Now in this question 2.2, we want to find the value of the capacitor in this location so that it could produce the desired capacitance, which is equals to 2 microfarad in this circuit. Now, the first step here, we need to combine and resolve the equivalent capacitance. So let's start with this here. As you remember, if the capacitors is connected parallel, so we could resolve it in terms of the series, which means that this part, the C equivalence, will automatically equals to the sum 2 microfarad plus 4 microfarad, and which is 6 microfarad. Alright, now let's write it again to make it simple here. So we got the C and we have the C equivalence here, which is equals to 6 microfarad. Now, what do we have here? To resolve this case, we need to use the parallel formula, which let's write the C equivalent 1 and the upward 1. In this case, it will be C times the C equivalent, and all divided by C plus C equivalent, which this C equivalence on your left here, this is CT, as you know from the desired total capacitance. So let's substitute the value, which we'll get 2 microfarad, and then C times 6 microfarad divided by C plus 6 microfarad. So then we will get 2C plus 12 equals 6C, 4C equals 12, and C equals 3 microfarad. And that's the answer. So that we want to find the value of this C, which is equals to 3 microfarad. Let's take a look at this question 2.3. We have the current in a 10 millihenry inductor, which is shown in the following circuit, as you see according to this graph. Now what we want to do is we want to find the voltage across this inductor, or we want to find the graph that represents this relation between the voltage and the time. So in that case, first of all, we got that this inductor we have 10 times 10 to the power minus 3 Henry according to the question. And from the property of the inductor, we got that the formula of the voltage across that inductor at a specific time is equals to the inductance times the derivative of I dot the current upon 2 at that time respected to t. In that case, you can divide it from the graph, right? We can divide it into 1, 2, 3, and 4. So we're going to find the voltage in 4 parts here. And we could also include the last part as well, but as you can see that the current that changed in time is equals to 0. So this part we could automatically say that it is equals to 0 as well. Now let's find in each part, starting with the voltage at 0 to 2, the time from 0 to 2. So in this case, the change of I respected to t is also equals to the slope in this case, because you know that when, for example, in a simple equation of the line equation, because you can see that it's a line equation, right? Y equals the slope m times x and plus the constant b, and when we derivative I divided by x, we will get the value which is the slope itself. So let's apply this concept to each part here. Then from the time 0 to 2, we will get that the voltage is equals to 10 times the value of the inductance and the slope itself, which according to this graph, we know that it is at the end is the value of the current is minus 10, the starting is 0, and all divided by time difference, which this result in a 50 times 10 to the power of 3 volts, or it's equals to minus 50 millivolt. Alright, seems like I'm right this answer a bit too big. Let's resize this part as well. Alright, for the second part at 2 to 4, we do it similar steps here. The slope in this case is going to be positive, which is equals to 5 minus at this location minus this location. So we get 5 minus 10 and divided by 4 minus 2, which is equals to 25 millivolt. And the case for the third part, 6, which you could actually see that the change of the current here is constant. So we could assume that is equals to 0 automatically. And the last part, the last part here, from the time 6 to 7 here, which is equals to 10 the inductance times the difference of the slope itself, which is equals to 5 minus 7 minus 6, and in that case which is resulting in minus 15 millivolt. Now that we got every part, now let's create a new graph that represents this answer. Remember that this unit is millivolt, so please specify that too, unless you want to get deducted in the score. Alright, so the first part from 0 to 2. As you know that the value from this part, because I may forget this, but in the linear equation, the derivative of I respected to t is constant, as I have already shown in this linear equation. So we could say that this value of voltage is constant in this duration, and then it changed to 75 for about 2 to 4 seconds, and then it come back to 0 for another 2 seconds, and at the end it go back to minus 50 for about 1 second, and then it returned to 0. So this part is time in millisecond, and this is the voltage across the inductor, which represent how the current flow from according to this question. In this question 3, we want to solve this following circuit in two methods, one that using the nodal equation, the nodal analysis, and the one that use the mesh analysis. So it's going to be long in this video, but if you guys follow through these steps, I'm ensure you that it's going to be easy enough. So let's start it by duplicate a circuit, one that is going to be used for the nodal analysis and the one that is going to be used for mesh analysis. So starting with, we need to specify each node, right? Which we have this node here, the one in the middle, on the right, and the end here. This node, we can represent it as V1, V2, V3, and also this is the ground. As you can see that it's connected to the ground, so the VG is automatically equals to 0 volt. Alright, So the first step here, let's look at this here. You see a node, or let me use another color. You see a node that has been on the left and the right side of this component, the source here. It is the supernode, as you remember. So the supernode here, we use the Kirchhoff voltage law, and we could solve that V3 minus V1 is equals to 10. This is the first equation. Our objective here, we want to find V1, V2, and V3. So we need 3 equations at least. Alright. Now the other 2 equations, let's look at the head and the tail of the supernode here. When we focus this part here, we could say that it's a current that flows through here. We could represent as I1. The current that go out, I2. The current, another current that go in here, I3. And the current that flow out, I4. So let's say that apply KVL and KCL, Kirchhoff current law, at V1 and V3. So what do we get here? We get the total sum, the current that flow here, I1 plus I3, and the current that flow out is I2 plus I4. Alright. Now, what are we going to do next? We use Ohm's law. Then what we have here is that the I1 is equals to minus V1 divided by 4, and I3 equals to V2 minus V3 divided by 2. For the I2, it's going to be V1 minus V2 divided by 2, and the last part, V3 divided by 8. Now, let's simplify this equation. So, at the end, it's going to be 6V1 minus 8V2 plus 5V3 equals to 0. So this is the second equation. Now, we need another equation so that we could solve this problem. And as you see, the last part is in the middle. And using the same law, the KCL, and Ohm's law as well, KCL plus Ohm's law. I need to clarify more something. In this case, there is no KVL, sorry about that. And the way we use KCL, as you can see, that the current that flows through this point in and out of the supernode is considered in this case. And when we use Ohm's law, because Ohm's law from V equals IR, right? And we know that in this case is the difference in voltage and divided by the resistor at that current. So apologize for that case. Now in the second part, we have the KCL plus Ohm's law, right? So what we have here, at V2, we have I2 and plus 5, oh my bad, I2 plus 5 equals to I3 from the Kirchhoff current law, right? Then use the Ohm's law, we will get V1 minus V2 divided by 2 plus 5 equals to V2 minus V3 divided by 2, which resolving in V1 minus 2V2 and plus V3 equals to minus 10. This is the third equation. Now combining all three equations, combining it in metric form, then starting from the first one, we get minus 1, 0, 1. The second one, 6 minus 8, 5, 1 minus 2, 1. So this is the metric equation from it in terms of using nodal analysis in the first part. Now let's take a look at the second part where we use the mesh analysis. So from this part we need to identify the mesh in this circuit. So you can see that it's a 3 mesh. The mesh, remember? 3 mesh here. We could specify the current that flow in clockwise I1, I2, and I3. Now let's starting from the first one, the mesh in the mesh 1 here. By using the Kirchhoff voltage law and Ohm's law, what we get is that starting from the first one, minus 10 plus 2 times I1 minus I3 and plus 2 times I1 minus I2. If you guys confused, look closely that there is a current that flow in the opposite direction at this part and this part. Let's take that in consideration. So this resolves in 2I1 minus I2 minus I3 equals 5, the first equation. Similarly to the first part, we need 3 equations to resolve this problem. Now let's take a look at the second mesh. As you can see, so you see that there is a current flow in the middle. The current flow in the middle. So what we get here is a super mesh. A super mesh, we can consider the overall using the KVL and the Ohm's law, and then we could use the KCL in the middle later. So let's write a new mesh again. And don't forget that each part has the I2, I3, and the above is I1, don't forget it. So we're applying the Kirchhoff voltage law and Ohm's law again. In that sense, we would have 2 times I2, don't forget it, minus I1 plus 2 times I3 minus I1 is 8 times I3 and plus 4 times I2. Now this will resolve in minus 2I1 plus 3I2 plus 5I3 equals to 0. This is the second equation. Now let's look at this again here. The total current flow in the middle is 5, and we have I2 in this direction and I3 in this direction. So by using the Kirchhoff current law, we get that I3 minus I2 is equals to 5. And this is the third equation. Yeah, now let's combine it in the last part. Combine 1, 2, and 3 in metric form. This is really important when you're doing an exam or anything else, because this is your final solution, your final answer to represent what you have been doing so far. Then we get 2 minus 1 minus 1 minus 2, 3, 5, 0 minus 1, 1. Alright, so, and that's it. We combine everything else and then we get the solution in terms of metric form using mesh analysis. So from these two solutions here, there are advantage and disadvantage depending on the circuit itself. So if you see more mesh, you probably use the mesh analysis. But if it has less mesh, you could use total analysis in another case, which could resolve easily or resolve easier than the other solution, depending on the question and the circumstance. And that's the end of question 3. Thank you.
4. Circuit theorems. Consider the following circuit. A. Obtain the Thevenin equivalent circuit at terminal RL. To find the Thevenin equivalent circuit at terminal RL, we need to find the Thevenin resistance, as well as the Thevenin voltage across those terminals. We can find the Thevenin resistance by removing the load resistance, leaving an open circuit in place, then turning off all independent sources in the circuit. Remember that a current source becomes an open circuit when turned off, and a voltage source becomes a closed circuit once turned off. We can redraw the circuit as follows. Then, we can find the Thevenin resistance by combining the remaining resistors into one, using various resistor combination rules. Firstly, we see that these 1 kΩ resistors are in series, therefore we can simply add them together into 2 kΩ. Next, we get a couple of 2 kΩ resistors connected in parallel, so we can combine them using the parallel rules for 2 resistors. R1 times R2, divided by R1 plus R2, this gives us a 1 kΩ resistor. Lastly, we get a couple of 1 kΩ resistors connected in series. Adding them together yields a 2 kΩ resistor. Thus, the Thevenin resistance is equal to 2 kΩ. Next, let's find the Thevenin voltage. Redraw the circuit with the load resistance removed, then denote the 2 remaining terminals as positive and negative. The Thevenin voltage can be found by finding the voltage across these terminals. Here, we may use any applicable theorems to help us find the voltage. In this case, we will use the nodal analysis in tandem with Ohm's law. We start by finding all nodes in the redrawn circuit, then mark one as the reference node, or the ground node. Then, we denote unknown currents on each resistor with arbitrary directions. Next, notice that by choosing the bottom node as the reference node, node A, we'll have a voltage equal to the voltage source, which is 12 volts. That means we only have node B and node C left to compute. Next, we will use the Kirchhoff's current law on each remaining node. Node B has current IA, and for milliamps flowing in, and current IB flowing out. Therefore, we get that IA, plus for milliamps, equals IB. Node C has current IB flowing in, and current IC flowing out. Therefore, we get that IB is equal to IC. Then, using Ohm's law, we can describe each unknown current in terms of voltage and resistance. IA travels from node A to node B, over the 1 kΩ resistor. Therefore IA is equal to VA, which is 12 volts, minus VB, over 1 kΩ, or 10 to the power of 3. IB travels from node B to node C, over the 1 kΩ resistor. Therefore IB is equal to VB, minus VC, over 1 kΩ, or 10 to the power of 3. IC travels from node C to the ground node, over the 2 kΩ resistor. Therefore IC is equal to VC, minus V ground, which is 0 volts, over 2 kΩ, or 2 times 10 to the power of 3. Substituting them back into the original equations, we can now solve for the voltage at node C, which is equal to the Thevenin voltage. Therefore, we get that the Thevenin voltage is equal to 8 volts. We can now draw the Thevenin equivalent circuit at the load resistance as follows. B. Calculate the current if the load resistance is equal to 8 kΩ. By using the Thevenin equivalent circuit obtained from Part A, we can find the current by simply using Ohm's law. The voltage is equal to the Thevenin voltage, which is 8 volts, and the resistance is equal to the Thevenin resistance, plus the load resistance, which equals to kiloohms, plus 8 kiloohms. Finally, we get that the current at the load is equal to 0.8 milliamps. C. Find the Norton equivalent circuit. To find the Norton equivalent circuit at terminal RL, we need to find the Norton resistance, as well as the Norton current across those terminals. Since we already have the Thevenin voltage and the Thevenin resistance, we can use that to quickly find the values we need, through the relationship between Norton and Thevenin's theorem. Firstly, the Norton resistance is equal to the Thevenin resistance, which means that the Norton resistance is equal to 2 kiloohms. Next, the Thevenin voltage is equal to the Norton current times the Thevenin or Norton resistance. Substituting the values we already know into the formula then yields the Norton current, which is equal to 4 milliamps. The Norton equivalent circuit is a circuit with a current source equal to the Norton current, a resistor equal to the Norton resistance, and the load resistance, all connected in parallel. Therefore, we can draw the circuit as follows. Lastly, D. Find the maximum power transfer that can be delivered to the load RL. The maximum power transfer to the load RL can be found by the formula Thevenin voltage squared divided by 4 times Thevenin resistance. Substituting in the values and computing then yields the maximum power transferable to the load, which is 8 milliwatts. 5. Operational amplifiers. Find the output and I output in the following circuit. First, let's recall the properties of an ideal operational amplifier. 1. The the voltage at both terminals, positive and negative, are equal. And 2. The current flowing into each terminal is equal to 0 amps. Next, let's identify and mark all the nodes in the circuit. We will mark the nodes at the input terminals of the operational amplifiers as V- and V+ accordingly, and mark the bottom node as the ground node. Next, notice that node A and node B lie across each voltage source, with the other side connected directly to ground. That means we can immediately identify the voltage of both nodes. Node A has a voltage of 5 volts, and node B has a voltage of 4 volts. Let's identify the voltage at V+. Since the current flowing into the terminals of an ideal operational amplifier is 0, the loop consisting of the 4-volt source, 5 kΩ resistor, and 20 kΩ resistor are isolated as a series circuit with a single voltage source. Thus, we can find V+ using the voltage divider formula, which states that the voltage across an element in a series circuit with a single voltage source is equal to the voltage from the source times the resistance of that element, divided by the sum of all resistances in the circuit. In this case, the voltage is equal to 4 volts, the resistance is equal to 20 kΩ, and the sum of resistance is 20 kΩ plus 5 kΩ. Therefore, we get that V+ is equal to 3.2 volts. And that V- is also equal to 3.2 volts. Next, we will use Kirchhoff's current law and Ohm's law to find V output. Let's look at the current at V-, denoting the current flowing over the 5 kΩ resistor as I1, and the current flowing over the 40 kΩ resistor as I2. We see that I1 is flowing in, and I2 and 0 amp is flowing out. Therefore, I1 is equal to I2 plus 0. Then, we'll use Ohm's law to transform I1 and I2 into terms of voltage and resistance. I1 travels from a node of 5 volts to V-, which is 3.2 volts, across the 5 kΩ resistor. Therefore, I1 is equal to 5 minus 3.2, divided by 5 times 10 to the power of 3. I2 travels from V-, which is 3.2 volts, to V output, across the 40 kΩ resistor. Therefore, I2 is equal to 3.2 minus V output, divided by 40 times 10 to the power of 3. Substitute both formulas into the original one and compute. Therefore, we get that V output is equal to minus 11.2 volts. Lastly, we will also use Kirchhoff's current law and Ohm's law to find I output, where I output is the current output from the operational amplifier. Looking at node V output, we see that there is I output and I2 flowing in, but no current flowing out, as the terminals are open. Therefore, we get that I output plus I2 equals no current, or 0. Substituting the formula for I2 and the value of V output from previously into our new formula, we can calculate I output as follows. Therefore, we obtain that I output is equal to minus 0.36 milliamps.